If you look up in the universe and feel small, it's because you started out with an ego unjustifiably too high to begin with. So yes, it is ego busting. Yes, to learn, no, Earth is not the middle of the universe, neither is the sun, neither is our galaxy, and you're small, you are in time and in space. That's all true. But the cosmic perspective takes a step beyond that, and it allows you to realize that, the atoms in your body, the molecules that comprise life, are traceable to stars that manufactured those elements in their crucibles of their core and then exploded, scattering that enrichment across the galaxy, enabling next generations of stars to form planets, and at least on one planet, life, and at least at this time, people. So we are a participant in the great unfolding of this cosmic story. So people like to think I'm special because I'm different, but there's a whole other way to look at it. Maybe you're special because you're the same. So if you go into the sun, here are these X-rays. They have such energy. These are photons of light. They have so much energy. Energy goes up with violet, ultraviolet X-rays, gamma rays. It goes up. It goes down in the other direction. It has so much energy that you can ask, what happens if you plug that energy into the equation equals mc squared? Just do that. If that's the energy on the left, what mass equivalent is that? And you know what you find out? It has so much energy, it could spontaneously make matter. It can make a pair of electrons on its own. So in the center of the sun, matter is being forged out of the soup of energy every moment of the sun's life. What kind of matter does it make? It makes an electron and an anti-electron, a positron. Matter and antimatter pair. Antimatter is real. So when you have a high enough energy for the light, it will spontaneously become matter, and the matter-antimatter pair come back together. It makes the X-rays again. It's a soup. That's unfamiliar to us. We don't see that. Visible light doesn't do that. It's not energetic enough. It just stays as light or gets absorbed, but doesn't become energy. It doesn't become particles. In the early universe, this went on big time. And it's one of the symmetry laws of particle physics that light becomes two particles, matter and antimatter. You bring them together, they become light again. It's always symmetric, always. Yet, we're made of matter. Where's the antimatter? So there's some discussions that if an alien came and landed from another galaxy, before you shake its hand or whatever appendage it's offering you, flip it a coin. If the alien spontaneously explodes, it's antimatter. Just always be ready to have something else touch the alien. So something happened in the early universe to create an asymmetry. It's one of the mysteries of the early universe. 1 out of 100 million of these particle-antiparticle pairs, 1 out of 100 million of them was just a particle and not the antiparticle. 100 million. I mean, it's rare, but it happened enough to account for all the matter that we know and see and love in the universe.
Stephen Hawking showed just recently, and for me this was kind of spooky amazing, that black holes remember everything that they have ever eaten, which means it's not a tunnel to anywhere. Everything that it ate is sitting there at the singularity at its center. The spooky part is, Stephen Hawking showed 40 years ago that black holes can actually evaporate. The matter that's within a black hole can rise up out of the gravitational field that surrounds it and spontaneously birth a pair of particles. That's just E equals mc squared doing its thing. E equals mc squared. The gravity field has high energy density. Out of that pops particles, and those particles escape, taking matter away from the black hole, from the gravity field of the black hole.
Doesn't that fly in the face of how we think of a black hole?
Yes.
A black hole, gone forever.
Yes.
Because nothing escapes, because nothing has surpassed the energy needed to go faster than the speed of light.
Except quantum mechanics, this quantum physics from the 1920s gets you out of that problem. That's a classical understanding of black holes. You layer quantum mechanics on it, weird stuff happens. Completely legitimately weird stuff happens. Quantum physics is kind of magic because none of it issues forth from your common sense. Particles pop in and out of existence. One time it's a wave, the next time it's a particle, and it interacts with itself. And you measure it here, but it shows up there. If we were forged in that world, then all that would be common sense. N equals mc squared would be a daily phenomenon. You would need Einstein to figure it out. You'd be learning it in elementary school. But that is a foreign universe to us. And so what goes on there, you are prone to say, that doesn't make sense. You know something? It's of no obligation to make sense to you because your senses didn't come out of that universe of tiny particles. We don't live there. If you let something go and it drops, you say that makes sense. If you let something go and it goes up, you say that doesn't make sense. In quantum world, that happens all the time. It would make sense in the quantum world. So I submit to you that if I take your body and dump it into a black hole, what Stephen Hawking showed is that all the particles that went into the black hole, let's say it's Stephen Colbert black hole, okay? No other contaminating bodies but your atoms in the center of this black hole. And I wait around, and out here in the gravity field, particles pop into existence. And I make a check. How many protons? How many neutrons? How many electrons? How many neutrinos? By the time this black hole is evaporated, it would have been every single particle that you were having fallen in the first place. Extracted out of the energy field of the black hole. So it remembers who you were even out in the gravitational field. That's spooky to me.
The universe had a birthday 13.7 billion years ago. So imagine a universe that is infinitely large. Now, put yourself in the middle, and I tell you, this universe was born 13.7 billion years ago. So let's go out to the circle, to the sphere around us, go to the spot that's 13.7 billion light years away. In other words, go to the spot where light from objects has taken 13.7 billion years to reach you. You're gonna be watching that object being born because its birth light is just now reaching you. Come in a little bit. You're gonna see those in their toddler years. Come in a little, they're in the adolescence. Come in a little closer. Come to the present day and you see everyone in their modern day maturity. So there's a limit to how far you can see in an infinite universe if the universe had a birth date and the speed of light is finite. Wait a billion years. Now the horizon is 14.7 billion light years away. Now you're seeing those galaxies get born. So the interesting thing about the universe in which we live, as long as there's galaxies that get overtaken by this expanding horizon, you will always bear witness to the birth of the universe because somebody is always being born. The interesting part is if the signature of the Big Bang goes away, that would tell you that your horizon washed over a region of the universe where there are no more galaxies to show you their birthday clothes. That would tell you that you in fact reached the edge of the universe. Right now, we can only tell you about the edge of our horizon, but that is an ever-expanding horizon that's still delivering up the signature of the Big Bang.
What happens when the galaxies over there are really, really far away from the galaxies over there? So if you...
Everybody's got their own horizon. So we are on the edge of a galaxy's horizon 13.7 billion light years in that direction. They see us, our light from 13.7 billion years ago is only just now reaching them. So they see us going through the birth of the Big Bang. We are their Big Bang signature right now. So everybody's got their, just like every ship at sea has its own horizon around it.
How does it happen that we don't experience this expanding of the universe as we walk down the street or sit here in this building?
Yeah, I think about things you miss because of how short our time on Earth is. The best example I can give is when you walk around and say, oh, there's a nice puffy cloud. You don't stare at it for an hour, you just notice it. If you do a time lapse of the clouds, especially cumulus clouds, they are roiling, gurgling, boiling places of condensed water vapor. They're alive. Yet when you walk down the street, you think it's just sitting there peaceful and calm if it's just a simple cloud. So even something that does change in your lifetime, you don't think of as an actively roiling place, a cloud. So imagine mountain building on Earth. Imagine watching the Hawaiian Islands pop up or come up. Imagine watching ice ages come and go. Imagine watching species of life rise up, the dinosaurs, and then an asteroid comes, they go extinct, essentially overnight in the fossil record. That's a whole other way to see the world. And it's the task of the geologist, the astrophysicist, to think about how that works. Fortunately, we have computers that can speed up time. I'll give you a great example. We used to have catalogs of galaxies. Let's say that's a really messed up looking galaxy there. Let's make a catalog of irregular galaxies. So we have a catalog of beautiful galaxies and irregular galaxies. And then people came up with theories. How does a galaxy become irregular? No one knew until we realized galaxies collide. Galaxies feel each other's local gravity, collide, and it's a train wreck. And half the irregular galaxies are train wrecked galaxies. So we would learn. Now, how do you get to know that galaxies collide? You put in the forces of gravity on a computer, run the simulation, and watch it unfold. And there you can recreate the havoc that you see in the universe on 100 million year timescale.
Tweets, what obstacles do we have to overcome in order to facilitate interplanetary travel?
Oh. Okay, you know, Voyager just left the solar system. The Voyager spacecraft, it was in all the news a few weeks ago, traveling fast, all right? And it's at this boundary between the sun's influence and the galactic influence. And so you can say, well, if you hitched a ride on that, how long would it take you? Because that's been going for 40 years. How long would it take you to get to the nearest star? The nearest star. in a galaxy that has 100 million stars in it. 100 billion stars in it. The nearest star take you 40,000 years. So the question, what does it take to become interstellar space? We either have to figure out a way to live a really long time or send a crew of astronauts that are really fertile so that the 80th generation down the line is the one who lands at the destination, or we have to find out something new about the fabric of space and time so that we can basically invoke the famous warp drive engines that are common in Star Trek, allowing them to cross the galaxy during the TV commercial.